different ways, you know.
Yeah.
I mean, there's all sorts of different ways you can plot things. You can plot things R1 versus temperature and have different frequencies here. I mean, yeah. You can have R1 versus molecular weight and have different temperatures, different frequencies.
Just try to show a relationship between them.
You can try different things. And one of the things that people do, one of the things you should get into a habit of doing is essentially what is playing. You know, just trying plotting one thing against another, you know, plotting everything against everything. And quite often you can make discoveries in life where you plot it one way, you get kind of gibberish. You plot it another way, you get gibberish. Plot it one way and you get this beautiful straight line. And you think, what just happened? And then you think, well, why, when I plot it that way, do I get this beautiful trend or something? And that's it. Then you start. That gives you a way. Then gives you a way into thinking. You go, well, there must be some connection between this parameter and this parameter that makes this happen. You know. So you know, and then you're always going to have trends like it'll go one way temperature, or does it always go? Does it jump around with temperature? Does it systematically go one way or the other way? Then you have to ask yourself, why does it always go that way with temperature? Maybe it has a minimum, maybe it goes up with temperature, then back down with temperature. Why is there a maximum or minimum? You know, when I plot it with frequency, it's monotonic, it always goes down. Why is that? Maybe it goes through a minimum. You know, so you should always play and then ask yourself, why is it doing whatever I've just found it doing? You know, do I understand that? Does that make sense?
And you know, because it goes like to 10 kilohertz to 10 megahertz
Yes.
is a range.
Yes. So you need to plot on the log axis.
I've noticed that the when we run the data for the software, it only gets 20 points.
Yeah.
Is 20 points enough?
Well, it depends. There's no correct answer for that. It depends on what it looks
Because
like.
if you're doing 20 points in between these two things, you could miss.
Oh, you can always miss things. But then you've got to, I mean, you're right. You can always miss things, okay? And there's no way to know that you haven't missed something.
Unless you do every single point.
Which you can't do. So there's no way to know that you haven't missed something. So what I mean is if a curve looks like that, you know, then 20 points is easily enough to kind of
get the idea, yeah.
If the data really does, if this is what it really should look like, I mean that's not noise, that's real. 20 points is not enough to map that. You know, you get something that does this, and you've missed all the features. So there's no way of knowing. You have to look at it, you know. And you are right. Even though you get this, who knows? Just between these 2 points, maybe there's a big spike that you've missed.
Yeah.
You know, but that's like saying there's a dragon in the coal shed behind you. You haven't seen yet.
Okay.
There could be a dragon in there, but. You know, and you don't go around checking every coal shed just in case there is a dragon.
And this frequency, that's the signal that you're supplying to the sample.
Okay, that's not. No, well, it depends what you mean. My first reaction is no. What it is okay.
So can I just run through how I think the machine works, and you see if it's hand wavy right?
Okay.
It's like the magnetic field. It'll split up all the energy levels.
Yeah, there's only two spin-and-a-half particles. There's only two.
Yes, and then so you apply a signal to that, and it goes up, and then you're measuring the.
Well, also, by the way, just to correct you, you're right in what you're saying. You have a proton is a spin-and-a-half particle. Okay. What does that mean? It means it has two energy states. That when you put in a magnetic field, those energy states.
Does it even affect 2 plus 1?
They actually got the same energy level when the B field's 0, but they're different. We often pictorially call this one spin down and this one spin up. Okay. That's a bit misleading, but what the heck. When you put a photon in of the right frequency, which corresponds to this energy gap, so that the energy gap, let's call it delta E, equals HF or H bar omega, using different language, but same thing. Then, this is where I'm correcting you. You can cause this to happen, but it also causes that to happen as well. It's not just that you pump them up, you can knock them down as well. It causes transitions in general. Okay. And in fact, what's really interesting, they're up and down and up are equally likely. And
then you just working out the decay time for it to go back to where it was.
Yeah, so basically, there's a Boltzmann distribution. So when you have a magnetic field, this is slightly higher energy level, this is slightly lower. Okay. So if you have a Boltzmann distribution, that means you'll actually have slightly more in the lower energy than in the upper one, like that. Now the difference is, that's exaggerated. The difference actually, I'd have to draw 10,000 of these, yes?
Right.
And then on top I'd have 9,999. That's the difference, roughly speaking. Okay.
Why is it 10,000? Because it's 10,000 protons.
No, I was trying to emphasise what 1 part in 10,000 is.
Oh, sorry, okay.
So there's a 1 part, here I've got, 2 in 5 are in the higher energy level. So 2 parts in 5. what it really is that for every 10,000, roughly speaking,
Yeah.
that I have pointing up, I have one less
In the down.
pointing down. That's how small. The energy difference is so small that basically the up and down states are equally populated. Just not quite. About 1 part in 10,000.
So it could fluctuate itself.
Yeah.
Yeah.
But I mean, you've actually got like a 10 to the 24, just as a guess, nuclei in there. So actually 1 part in 10,000, when it comes to 10 to 24, corresponds to an extra 10 to the 20 nuclei in the down state, which means that's a gigantic number.
Yeah.
So you actually get a big signal.
Yeah.
Okay, and so but still, nevertheless, it's only 1 part in 10,000 that it has higher energy than the lower. It has the lower energy than the high energy.
So, if this is characteristic, obviously, for the splitting, why shouldn't only one work?
So what we do is we then. So what you're actually doing here, that's where you. I didn't agree with you because now I know that you're wrong. Is that this frequency here? Okay, is this frequency here? You're right. That bit is correct.
Yeah.
Okay, but this gap here depends on the B field.
Is that not constant?
Exactly. That's exactly what is not constant in this experiment. That's exactly what you actually are varying here. You're varying the strength of B.
Is that what that is?
F is this F,
Okay,
which
yeah.
is proportional to B, and it's B that you're varying, which means that the F that you have to use to cause things to happen has also varied. This is the F that you have to use to make things happen, which means the B has changed.
So it's changing
It's changing
proportionally
B.
with each other.
It's changing the B. Yeah?
So as F changes, B changes as well.
No, B has changed. Let's do it the right way around. B has
Right.
changed, which means you have to use a different F.
Okay, so if they both change the same amount, why would T change?
Well, that's a different thing. Now so now you've understood that what we're doing is we're varying B, which is varying the size of this energy gap,
Yeah.
which means we have to use photons of a different frequency, and actually this is what this frequency is talking about. Okay.
And then you just see how long it takes to get back.
Yeah. Now it turns out that T1 is dependent on what causes T1. That's the next question. What makes something relax? So you've got the idea. You've got something in equilibrium. Okay, that's your sample sitting in a magnetic field. It's in equilibrium. That means there's some distribution like this, which is the equilibrium distribution. Then you come along, you put a photon in just the right frequency, you pulse it, which causes transitions, which means you disturb the equilibrium. So after you've pulsed it, it's no longer in equilibrium. You got that?
Yeah.
T1 is a measure of how long it takes for the system to recover to equilibrium, roughly speaking. Yeah? Okay?
Oh, I get you now.
So T1 is a measure. It decays exponentially, so it takes T1's amount of time to recover back to equilibrium. You got that? The next question is, why does T1 depend on frequency? Okay, well, why does T1 depend on this energy gap? Or why does T1 depend on B? They're all the same sentence, just said differently. Got that? Well, the question you have to answer first is what is T1 dependent on, and why is it dependent on things? So what is this? What is the spin lattice relaxation? That's what it's called. Dependent on. That's the question. That's the question.
I thought it would be. It makes sense to depend on the splitting, like how big the splitting is.
Does it? Why?
Because if it's further, you'd think if it's further away, it's going to take longer to get back to what it was.
I mean, I can see.
Or
What
if
you're
it took
saying
a high amount of energy to take it away, it's going to take. I don't know actually.
So that's a question to ask yourself. Okay, you can do that as part of the research. What are the microscopic things that are going on, inside your system that affect T1? Some samples have a very long T1, some samples have a very short T1. When you change temperature, you will change T1. This is what you'll notice. When you change the molecular weight of your sample, you will change T1. So since molecular weight and temperature are ultimately microscopic things, they're telling you how quickly things are moving. Same molecular weight, think about it. Bigger molecular weight doesn't move quicker, it's going to move slower. So there are different ways of making things move quicker and slower. How come that affects the T1? That's the question.
Does anyone actually know?
Yes.
Is that the research for?
No, that's well known. That's well known since the 1950s.
Oh, 1950s, you know what T1 is related to.
Yeah. And in fact, I gave you papers. I tell you what T1 is related to.
I got equation for T1 here.
No, that's not T1.
That's correlation.
That's the question. But yeah, I gave you papers on T1 theories, so you have to read them.
Okay, right.
Okay, so Cool. So, yeah, but now you've understood that at least.
Yeah.
And what that frequency really is the magnetic field strength. That's what that really is. Okay. Because people talk about alarm frequency, omega. Okay. And what that is, it's proportional to the field strength. So when people say, oh, I've got a 400 megahertz NMR machine, they mean this F hidden inside this omega, which is 2 pi F, is 400 times 10 to the 6. Which tells you this B is 9.4 Tesla. Okay. So for all these frequencies, you could actually work out the B from this relationship. Okay, that's just a constant for protons. It's called the gyromagnetic ratio. It's in one of my papers. Yeah. Okay, so that's.
So if we plotted 1/T1 with B, would we get the same shape?
It'd be exactly the same shape.
Yeah.
Because that's all F is. F is just proportional. F is proportional to B.
Constant that's changing it. Yeah.
Yeah. So the F is proportional to B. So yeah.
That's all my questions. If you haven't got any questions.
Have you any thoughts? Any worries? Do you know what you're doing next? That's the most important thing. That's the key thing. You go any measurements, and what's your first thing of the now? What's the once you imagine you've got some T1 data, you've put a sample in. What are you literally going to do first? That's the key thing, isn't it? Because you're going to have your data. Once you've done a measurement, you've got some numbers. So as soon as you've finished a scan, you have numbers. What are you going to do?
Start plotting some data.
Against what? What are you going to plot? You've got, you are. You've got some. What are you going to do?
R1 against frequency.
Okay, that's what the machine churns out. It gives you R1, doesn't it?
Yeah.
So there you are. You've got them. What are you going to do? There you are. You see what I'm saying? You've got to know what the very first, because otherwise you're going to have the data and you're going to be going, I've got data. You're stuck over here. You're stuck over here. You don't know what you're doing.
I thought we'd put R1 against frequency for different temperatures on the same graph.
Okay, so you're going to put different temperatures on the same graph. That's the first thing you're going to do. You have a look at that. Okay?
Yeah.
Yeah.
And you can see how temperature.
It's a qualitative thing. You'll see how temperature changes the R1.
And we can do the same for.
Would you be able to, once you've looked into these mechanisms for T1, what the origin, what's it depend on? Why does it depend on it? Yeah. You should then be able to explain what you see there, because it'll have some temperature dependence, and you should be able to go, oh, now that I understand what T1 is related to, it's obvious why increasing the temperature does whatever it does. And so you should be able to, in your lab book, write down a short paragraph saying, R1 did this with temperature, and that's because the things sped up as they got hotter, and that affects it like this.
Yeah.
Okay, good, cool. But in the paper that I gave you, the one that I put a little star on, which was the key paper, the one you asked for a second copy of, and I said, don't worry, you've got two similar versions. What does it plot? It plots T2 versus...
There was a B. I looked at the paper, I didn't see no.
I pointed at the graphs on the paper, I drew on them, I said this is the first thing.
Yeah, I've got the paper here. Is it this top left one you're on about?
No, that's not the first thing. Let's literally go through it. This is on the star on the left. I'll let you, that's the very first one. There you go. That's what you're going to do. Remember this? This is the first bit. You're going to pretend T2 is T1. We agreed to do that.
Yeah.
You're going to plot 1 over T1 against log molecular weight. And you've got a whole... This is only done at one frequency or one field strength. You've got the luxury of having 20, maybe more frequencies. But for each of those frequencies, for each and every single one, so you can duplicate this work by a factor of 20. If you've got 20 frequencies, you can do this. And then you fit that, and you obtain those two parameters. You then plot those two parameters as a function of temperature. That was what that graph, and the one you wanted to do has